Okay, so this is going to go over Munkers, the week 4. And so we're going to be starting out with the Cartesian products. And then we're going to go proceed into topology, and basis, part 1. All right. So our first definition that we're going to be dealing with is going to be introducing n-tuple, which purely is just, I guess, simpler than what the Munkers text has. Is just a list of n elements. And these are generally ordered, well, they can be ordered, but remember that's a list, so it's specifically going to be going off into specifically 1 through n. And these don't have to be specifically just 1 through n, they could be like 2, 4, 6, all the way until the 2 to the nth element, or I guess 2n element. And that's also a possibility. Um, this is just an example. And from this, we're also going to introduce something called a Cartesian product. Cartesian product. Which I guess an n-tuple of elements from each AI. So I guess what I mean by that, we could write this formally in form of like A1 cross A2 cross all the way until AN, and that's going to generate A1, A2, AN, where AI is going to be within each of those sets. And then some people also write this, especially if there's going to be a larger count, rather than writing individually 1, 2, 3, or all the way until n, we could just go ahead and also do the product of I equals 1, m, all the way until m of a I. And this is also going to generate, well, I guess if we make this an m, these are going to generate the exact same sets, or the exact same, set. Um, for those coming from like a calculation background, it's important to note that AI is a set, so I should specify that, meaning that we're doing a product of sets, and that's why we call it a Cartesian product. A way to think of this visually, you probably have seen this diagram, especially coming from like a calculus or like even just an algebra background, like a college algebra background, where you're drawing like inverse maps and like knowing what's, I guess you don't call it surjective or injective, but you're saying like one to one, one to many, or many to one. All of those maps are also, I guess, considered in this. In this case, we're having both a surjective map of all kinds. And it causes this pattern, which creates a mess, but we could formally think of this as this is like going to be the A set, and this is going to be the B set, and these elements are respectively. So then we have A1, B1, A2, or I guess let's just continue on with this ordering. A1, B2, A3, A1, B3, and then we go off into the next one, B1. And then we finish off with A2, B3, which I should have just written it. And this is going to be the exact same as A cross B, which is in itself a set. All right. So I guess one final way of just thinking about this is we could just think of this as all possible combinations all possible combinations in tuple. So I guess the question arises, what about A cross B cross C? And for those of you who might be really familiar with this, let's just choose any random element. So let's do A1, B1. Cool. And then we're going to cross with C because we have associativity. So we could also do this the other way around. Cross C1. And we just kind of standardize notation to write this A1, B1, C1. And that's just the, I guess, equivalence of that. And that's just due to, I guess, having some sort of equivalence relation. You actually not even an equivalence relation. Sorry, there's nothing about that, but there is just an associativity with that. The idea that people might get into is when you see this, I mean, it looks kind of abstract, but we could bring it down to a concept that we know. For example, R3, where we have X, Y, Z. Um, so X, Y, Z, and I guess this is a formulation of three elements, but that begs the question, is this the same as R cross R cross R, which is yes. So all these are going to be, well, these two are going to be the same. Yeah. And that's, I guess, like a little, I guess, Euclidean intuition behind R3. Of course, we might get into examples of that not being the case. We don't have to just deal with fields and number systems. But for now, I mean, we are going to just be we're just going to keep that in mind for now. So let's think of a new definition. Nope. For those of you coming from a calculus background, you may recall these tuples sequences being called, I guess, or these tuples themselves being called sequences. And generally, in like a calculus, you of course can have finite sequences, which are nice. They aren't that useful, but they're not bad. You might call these finite sequences, but specifically most of the time we'll probably be looking at an infinite sequence. And we generally note this as like a, first off, I guess an injection. So uh, 1 to 1, where we have 1 mapped to x of 1, 2 mapped to x of 2, and so forth. Generally, these create elements like x1, x2, x3, all the way off into infinity. Um, you can, of course, have these, I guess, if you have, say, a finite sequence, should also probably include finite. That's not very implicit. Then we could also have x here, and this could also be a 1-to-1, in which case we're just going to have to go with x1 all the way until xn. And that's also a possibility that we might deal with. When it comes to, yes, let's go ahead. Do this last part before we address a question that we had from the last lecture, which I thought was kind of interesting. When it comes to, I guess, addressing how can we do these one-to-one or surjective insertions, we generally want to consider cardinality, which is, I guess I like to think of it as the size. The size. Um, I personally, I mean, even in the lecture, you would hear me saying order a lot, which I don't know why. I am not being able to spell today. So these are kind of one and the same. The order of a set, the size of a set. Generally, order is a bit more relative than size of a set. And this is just kind of from an algebra background, so we don't really have to worry about it too much. So, a question that I had during the lecture, and I thought this was actually interesting. So, let's consider Euclidean spaces. Euclidean spaces. Okay. So, a student asked, whenever we're in linear algebra, we have Rn, or I guess let's go ahead and write this formally. We have the dimension of Rn equaling to n, and that's generally because these two match, right? Not always the case. It doesn't always have to be the case that, say, Fm, F is just a field, I mean, really anything, has to be exactly dimension n. Or I guess we should write this a lot more properly, dim of F if n is equal to n. Not always. Not always. So, and a more concrete example that we could actually think about is the dimension of just plain C. Or we could say C to the 1 if you really want to, but just C. C is in fact dimension 2. Dimension of C2, which we know is just going to be C cross C, by the way, is actually equal to 4. Okay, so if you continue down the list, it's just going to keep on going by like 6, 8, and so forth. So we're obviously doing 2s. And I guess what I explained that day, and also would like to reiterate, because dimensions themselves are going to be important in the future, especially when we're thinking about like I guess isomorphisms or up to I guess equivalencies of some kind in the future, which I won't really explain too much right now. We could think of C being isomorphic to R2. And so I guess the first question, if you haven't, I guess, taken linear algebra extremely well, or maybe your professor or the book hasn't explained it that well, you might go like, oh, why is it isomorphic to R2? Well, first off, you could actually map this out and do like the whole homomorphism, the injectivity, the surject, like the bijectivity of it all. You could of course check it like that. We're not going to do it, but the reason why is because we could actually just map R2 to C by taking A, B, and mapping it to, um, I guess, A plus BI. And that in itself is, I guess, the reason why it's isomorphic to R2. And then when we have C2, then we have to have 4 elements here, and it's A plus, or some form of right here, A plus BI in higher dimension, of course. Um, and that's, I don't know, I thought that was that was a really nice question, especially to build intuition, at least that I thought. Whenever we start dealing with further topics, I mean, you don't have to explicitly have algebra knowledge, or, I mean, of course you would have to have linear algebra at the bare minimum, I would say. But for those coming from, let's say, a linear algebra background, this is at least nice to have. Um, Regardless of us doing an intro to set theory to begin with. So, moving on. I actually did not prove this in my lecture. Yeah, I think this is actually an exercise question, funny enough. Finite, finite set. Then, yeah, I don't even know if this is in the text itself. Then there's a bijective mapping. Then there is not a bijective mapping. Um, a bijective to B such that B is not a complete set of, or a proper subset of A. And you could write it either this, or some people write it prop underneath. But overall, I'm just going to be using this notation to denote a proper subset because that's just how I personally learned. Some people just stick by B subset A and call that a proper subset. I think it's a bit too lackluster and leads to confusion. So I didn't provide this proof during the lecture, so for those who I guess wanted to skim through this, which I'll probably announce in the chat, um, this is a way to think about, I guess, the pigeonhole principle, which I just stated honestly. I just said it's due to the pigeonhole principle. I use this little diagram of like say B1, B2, and split each thing, B3, B4, and then you have A1, A2, A3, A4, and then you have A5, A6, and you have all these other elements that can't fit inside these boxes, and that becomes a whole problem. Um, but same exact idea, I guess a bit more formalized. Um, so let the cardinality of set A, this is going to be denoting cardinality. I didn't also explicitly say that before. So the cardinality of set A is equal to n, and let's say the cardinality of set B is also going to be m in this case. I mean, given that B is a proper subset of A, I think it is kind of implicit that B is going to be less than A. But I guess I just wanted to make this a lot more easier to understand. So let the cardinality of set A be A, n, and set B be m, where m is less than n. Let there exist m boxes dedicated to each of the m elements from, I should probably dedicate to m elements. Yeah, to m elements, to m elements from A. Given the set of A is equal to n, then there are n minus m, I'm going to specifically note that in parentheses, elements remaining from A that aren't in a box. Thus it follows that there is at least one box, one box that has two elements. Hence, by the pigeonhole, and this is purely what we did right here, pigeonhole principle, we have a contradiction. We have a contradiction. And I could explain this a lot further by saying due to some elements of B mapping to 2 plus elements. God, my handwriting is becoming messy. 2 plus elements from A. There we go. And I'm just going to write this as here. Cool. Whew. I'm going to open up a new page since we've finished our little section on, I guess, Cartesian products, and I'm gonna call this section specifically the countable sets. Let's see how much we could get out of it. So we're going to create a new definition of what is considered countable. Um, I personally don't quite like this idea or this notion of countability that Munkers proposes. We're going to follow it um, purely due to making future events easier. But I will give some intuition, perhaps, if I remember to do so, um, after I do this. So, and then we also have this countably finite. All right, and then we have this notion of is Q, the positives of Q, or I guess the non-zeros of Q, countable. And yeah, it is. And funny enough, we're going to be using our Cartesian product from Q2 or N2 all the way until Q plus, in which we could just map, for example, oh, got ahead of myself. We can map 1, 2 over to specifically 1 over 2. There you go. Yep. Generally, the way I like to think about countability is it's kind of like a sequence that you are doing some sort of, I guess, manipulation with at the end in order to generate the final set. That I like to think of it as. We see this as a two tuple or a pair mapped to single element, and we map the top and bottom. So if we had A, B, oh, A, B, then we could just map this to A over B. And of course, this doesn't just need to be positives. We made our lives a little bit easier, but we could also have like Z mapped to Q in some form or fashion. And that would also work. But the reason why we choose Q plus, I believe this part is specifically a homework question that you could do. Um, but or I think it's specifically, yeah, Q plus that has to be done. All right. All right. Where were we? Okay. So we have a lemma. So moving forward, I think this is going to be a question on the homework or homework. It's one of our Munkers questions. I don't believe I've assigned it though, because I think this kind of gives a explicit way that we could think of it easier. Um, so we have a lemma. Well, lemmas are, I guess, a way to say that they contribute to a theorem. Um, they're kind of like smaller little bite-sized theorems. They don't have to be bite-sized, but they're not big enough to be a theorem on their own. But a subset, and I actually did make this mistake in our lecture, of countable sets. I think I said a countable subset, which is wrong, is countable. There. All right. Um, and I think we just prove this, a proof theorem, actually. Oh, interesting. Guess I don't quite prove the lemma still, but it's not that bad. It really isn't. A subset of countable sets is in fact countable, and you could quite literally just think of this. I guess we'll see this specifically going to be in this theorem. Um, a countable, you should be able to, basically the idea is I don't even know if I provided this in the lecture, but the idea is basically just taking as many tuples as you want to just generate a singular element. A subset of countable sets is countable, or a subset of a countable set is countable. So, for example, let's just say, again, we're continuing with the idea of sequences, so we're having infinitely many elements, then you should be able to map it to some, like, I guess, function S of this countable set. So S of countable set, S of C. And we're going to say proper subset. Still is countable as long as it maintains its ordering in its final state. But a countable union of countable sets is countable, which should clearly be a lot more tougher to face. So this one, I think, I don't know if Munker's, I think this is also a Munker's like exercise or like example that it does give. But suppose that we have X is a countable set, countable, cool, and H, which goes from Y to X, such that NF is countable. I don't know why I did this in my specific proof, such that N is going to be within the naturals. I guess, yeah, I guess that's great. Thus, H is countable. I think I kind of rushed through this part. Maybe I was running out of time when I was writing this over multiple days. But specifically, I guess we're just taking a look at like if we have I mean you could replace this. No, you couldn't. So if you have, say, some element, yeah, um, some element y, which is possibly linked over to n, then you have your x mapping in itself, which we know f exists. So I think we should consider y some sort of form of combining f and n. Then we should be able to output that into here. So I don't know why we explicitly had this here. So maybe we should have in fact, um, perhaps y cross x here, y cross x here. And this should result in this NF over here, because recall that x itself is going to be our function, or is going to be our f itself, and y is going to be just our n value over here. God, that was a little bit messy, too messy for my liking. Well, ordering. All right, a set A with order relation is a WO set, and we're just gonna call this WO, such that the infimum of A exists within A itself. Cool. That's the best way to define a well-ordering set, that it has a least element that's contained within the set itself. That's perfect for us. Which means, does that mean that the reals are well ordered? No, but the positive reals are well ordered. But the reals does have an order relation. Cool. I guess if you do extend the reals, some people might do this. If you extend the reals with infinity, which is called the extended reals, then it is well ordered because you just have a negative infinity as our infimum of R. R infinity. I'm just going to call it that. And that's one way. That's one way some people think of the extended reals to allow well ordering. Um, I think actually Rudin does this. Rudin does do this, which makes sense. It is an analysis course. And finally, we get to our main goal, topology. All right. So I guess concerning this, Slender told me to be a little bit more explicit in my ideas of, I guess, my radicalization of what shouldn't be. Oh, is that? Oh, there you go. What shouldn't be. There we go. Or I guess what should be explained and what shouldn't be explained. I guess for I guess a topology course, since I believe he thinks that I was a bit too bare minimum. And I think someone also did say that in chat. There was a lot of questions, especially when we got to this area, so I'll try my best to be a bit more descriptive. I mean, keep in mind that we literally just started the actual topology section, so there's not really a lot to work on, to be fair. So topology on set X, and we're going to label this tall, is a set such that 1, the empty set, and X are both within tall. Cool. 2, the union of any arbitrary or I guess it doesn't even have to be arbitrary, but any subset of tau is in tau. And this is, I guess, formally written as the union of I in J of UI is within tau itself. Perfect. And then we have our third. Some people will sometimes combine the second and third, but I guess having it a bit more explicit here. The intersection of the finite subcollection of tau is in tau. And we could write this, for example, U1, U2 in tau implies that U1 intersection U2 is also in tau. And this can be extended to great detail. That's still here. This could be extended to great detail. Of course, you could think of this inductively, but this is just one example of such. And this is closure under arbitrary unions. And we could think of this as closure under finitely many intersections. All right. So I want to note something. Should I give an example of how a topology should look like? I guess we do give examples later on, but let me just give an explicit example. So let's consider the discrete topology. Discrete topology. So I earlier in our lecture, which I think led to a lot of confusion, I explained how we could think of topologies as, I guess, potential subsets. Well, they are subsets of power sets. So a discrete topology is a collection of all subsets of X, such that the size of tau is in fact going to be 2 to the power of X. X is, I guess, the size. This is just a denotation for power sets. Cool. So that means if we say have X is equal to 1, 2, 3, then the discrete topology of X is going to be, first off, X, phi. Those are always going to be included according to our rules. 1, 2, 3, and likewise 1, 2, 1, 3, 2, 3, and that's all. And these are all the possible sets. So given 3 elements, we should technically have 2 to the power of 3. So that's going to be 8. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And that's one way of thinking of topologies. Does it need to be exactly that? No, because we could also think of the trivial topology, which is the bare minimum. Quite literally, just tau is equal to X and phi, or X and the empty set. So I guess I want to also make clear how do we generate, what are these two topologies? And when we take a look at specifically our rules, the union of any arbitrary subset is going to be within tau. So the union 1 and 2 is going to be here. So I should probably, let me see if I can just point it out. So the union of 1 and 2, this is not great. Okay, here we go. That's better. So union of 1 and 2 is going to be right here. Perfect. The union of 2 and 3 is going to be right here, which is also great. Okay, what about X and 1? Okay, well, that's just going to be X in itself, so that's fine. X in the empty set is just going to be X in itself. The empty set in 1 is going to be 1 itself, so perfect. And then just the empty set alone, empty set is always just going to be the empty set. So I guess when we consider this trivial topology, we're only given 2 elements. Oh, we should also consider intersections, by the way. So the intersection of 1 and 2 is going to be 1, and that's an element of the set. 2 and 3, 1 and 2, 2, 3 is going to be 2, and that's also going to be an element of the set itself. If you're given, say, the bare minimum elements, you should be able to generate a topology with just filling in the blanks. Probably wouldn't be useful, but I don't know. That's, I think, just like a fun little exercise. If you're just giving yourself like 1, 2, and 3, what are the remaining elements? And for a discrete topology, and you just work it out. Cool. So now for trivial topology, how come these 2 elements are enough for making it work? Well, first off, we know that these 2 exist. That's a mandatory must. The union of X and empty set is just X. Perfect. The intersection of X and the empty set is just going to be the empty set. So there, it works. Cool. So I want to note that the elements of X, or the elements of tau, are called open sets. Cool. So each of these elements themselves are going to be open, and there is concepts of closed topologies. I don't know if Munkers, I don't recall if Munkers is going to explain that in the future, but in case it does in the future, I'll just go ahead and leave this, just calling all elements open for now. But there is such thing as closed sets, which I think Slender has mentioned before. Okay, so here's a fun little exercise. Let X be a top space. Then we're just gonna abbreviate this to be like kind of like topological space. And that's how it would probably be referenced later on because I don't want to say that mouthful every single time. So X is discrete if and only if for all X in X, the set of X is open. Perfect. And this is fairly short, I think. So first off, I guess just thinking about this intuitively, whatever is not in tall, because everything in tall is specifically open in this case, means that it's closed. Meaning if we take the complement of tall, meaning everything that's not in tall and isn't actually in set X, then those elements that are in set X and not in tall are going to be closed. So that means if it's discrete, every single element of X is going to be in fact open. Okay, how do we prove that? Because we're dealing with a if and only if statement, we're going to have to prove one direction first. So given X discrete, then X is going to be in tall, thus open. Cool. And then the backwards direction, the reverse direction, given for all X in X, X is open, then under unions and intersections, um, tall is, or I guess in this case, X is discrete. X is discrete. Cool. All right, perfect. All right, and this is a pretty well-known topology. Is it well? It's well known for one. It's a really beginner form of topology. Funny enough, I think yeah, no, it does have a name. It's called the uh, Pinsky topology. Sierpinski topology. And there's different there's special topologies that have attributes in specific sub-studies or a specific field in itself that are given a name because of how famous they are. Sierpinski topology, I would say, is generally a beginner topology that most people think about when defining these open and closed ideas. So given X is a set containing an open circle and a closed circle, and tall is a topology defined by X, the empty set, and this open circle. And I want to specifically say open and closed circle. Um, then the open circle is open. Cool. Hence, X is finite and not discrete. And the reason why we chose specifically the words open circle and closed circle is because this just so happens to be a closed element. Cool. Whew. All right. Yeah, this would be our last little, I guess, blurb. So definition, finite, complement, topology. All right, so X top space, Perfect. And we're gonna label this as tau of f to denote finite complement is all, I don't, u subset of x, and we're gonna say u can be, I guess, x itself, yeah. All right. Such that x set minus u is either x or the empty set, or sorry, not empty set, finite. Perfect. All right, let's think of a couple of things to think about, just like the bare minimum of finite complement topology. X set minus x is going to be empty set, which is finite. Perfect, so we know that exists. X set minus empty set is going to be x, which we know is also in our topology. So perfect. That's at least it's at least a trivial topology. All right. Suppose that that u is perhaps one of those elements. So if x itself, sorry, I should also preface, if x is finite, I think it's fair to say that it's trivial. Otherwise, I mean, if it's infinite, then we have some working to do because u itself also might be infinite. All right. And likewise, we also have something called a countable topology, which is another example. Not, I guess these two are not given the same name as after someone Sierpinski's topology, but we're going to denote this as T of C, such that x set minus u is countable. Which should follow easily, but I do want to also note here, I'm going to note here too, note if x is countable, then it's also trivial. And you might wonder why. X be uncountable. Why is this true? First and foremost, any subset of a countable set is countable in itself, which means u is always going to be included. Where is that lemma? Here we go. Any subset of a countable set is countable. And we proved that earlier, so that's perfect for us. Or we didn't prove it, but we stated it earlier, which is perfect for us. And we're done with that. Cool. So now we're getting into topic 13, or section 13. And this is going to be like, I think, yeah, just the bare minimums here. So definition, what is a basis? All right. So a basis for X is a collection for B, or sorry, for the basis B. I'm going to specifically write it in this kind of like math cal mode. Subsets. It's a collection of 4. I think I wrote 4 by accident. Selection B, subsets of X, such that 1, for all X in X, there exists B containing X, such that B is a subset, or B is also in this basis set. And 2, if X is in B1 intersection B2, then this implies there exists X in B3 such that it's a proper subset of B1 intersection B2. Perfect. Nope. All right. No. A subset U of X is open in X if for each X and U there exists B in our basis set such that X is in B, and B is a proper subset of U. In order to finish our lecture on our last little note for our proposition. So given that our basis sets is going to be a family of sets, UI, such that I is going to be in here. This is kind of like called the index. Subsets of X. Then ta of V is the topology generated by B. And maybe I shouldn't get too ahead of myself, but I kind of gave an example that sort of related to this question. Given by the union of I and J of UI, such that J is a subset of I, or collection of arbitrary unions of this basis set. Let's give a proper proof for this. Okay, so let's T be defined as this set itself. So I guess we could just choose the color red. I'm going to let T be equal to that. Then ta of this basis set, the topology generated by the basis, is going to be a superset of T. We know that phi is going to be within T because we could take the union of nothing. We know that X, so X, which is equal to U of I and I of UI. So X is in T. Cool. Then we now just have to prove intersections for all X in U1 intersection U2 implies UX is going to be within B, such that X is in UX, which is a subset of U1 intersection U2. Yep, U2. Perfect. Then U1 intersection U2 is also going to be within this union of all X's in U1 intersection U2 of UX. And so that also finishes our proof because we just now proved it's under all arbitrary unions of B. And that finishes our lecture for week 4. If you have any questions, please join the Discord server and feel free to ask. Bye.